The following is an introductory tutorial for Quick Machine. In this tutorial we will be generating a basic switch reluctance motor and analyzing it using FEMM. So in this tutorial I'm going to assume that you have installed both Quick Machine as well as FEMM. If you haven't, please go to the Quick Machine website and download and install both of these programs. Note that these two programs are the same. One is just for a 32-bit architecture and the other is for a 64-bit architecture. So once both of these programs are installed, please open Quick Machine and you should see something like the following. Now the first step in creating a model is to define the physical dimensions, and that's what this geometry tab is for. Now instead of going through each one of these one by one, I'm just going to load a motor that I've already completed. Note that the moment you finish each one of these inputs, the image on the right will automatically appear. And if I make a change to the inputs on the left, it will automatically change the picture on the right. So let me change this back. Now note that if you do not know one of the inputs, all you have to do is curse over the label and you get a visual representation of what the physical dimension really means. Alright. So now you may have noticed that some of these numbers that I've used seem very strange. For instance, the stator outer radius is 10 inches, but the stator inner radius is 75. But this isn't really inches. I'm saying that this is 75%. So in the case of the stator inner radius, the max that it can be is equal to the stator outer radius. So if I make this 75%, I'm saying that the stator inner radius is going to be 75% of 10 inches. So if I look, that's 7.5 inches. If I change this to 99%, right, the stator all but disappears. So let's change this back. So for each one of these percentages, it's essentially a percentage of a max, the maximum that it can be. So for instance, with the height of the tooth, right, so for this distance here, the maximum that it can be is equal to the stator outer radius minus the stator inner radius. That gives you this total distance all the way to the edge of this back iron. Alright, so for instance, if I change the height of the tooth to 99%, right, essentially all back iron disappears. So now one very cool thing about these percentage inputs is that when I change one of the inputs, it changes all the other ones in order to maintain these percentages. So if I take the stator outer radius and I change it from 10 inches to 20 inches, you'll notice that the picture on the right stays exactly the same. Right? It didn't change at all. Yet my stator inner radius changed from 7.5 to 15 now. Also note that if I uncheck this percentage button, then this parameter becomes fixed. And so if I change this again, say if I change this to 30, my inner radius does not change. It stays at 15. So now if I change this back to 75%, right? So this feature becomes very, very handy, especially if you're changing the scale of the motor, or if you want to quickly change the number of teeth but you don't want to fix each one of these dimensions. So for instance, like I did earlier, I changed this to 32 teeth, and it keeps each one of these percentages. So it makes it very easy to go through here and change the number of teeth, the number of lobes, as you can see. So I'm just going to change this back really quick. Alright. So once you have defined the physical dimensions of your motor, you need to then define the winding. Now the first step in defining the winding is to define how many turns are you going to have in your winding area. So I can do the turns in a number of ways. So for right now I'm just going to say that I have 50 turns. Now to actually define your phases and the angles at which your phases are firing, the easiest way is to just hit this auto set button. Now in later videos that'll be on the website, I'll go into detailed descriptions on how this auto set button actually works and what it's doing, and how you can go through and manually set these phases yourself if you have some sort of unique configuration. But this just gives you a standard phase winding. So notice that once I hit this auto set button, I have two phases which match the geometry of the symmetry, of the stator and rotor. Then also notice that these winding areas now have these numbers and letters. Right? So this letter here represents the phase that this winding area is tied to. For instance, this winding area is tied to phase B, and this number is the number of turns. Okay. Now note that the number might be negative, and that means that the current going through these turns are going into the page. If it's positive, that means that the current is coming out of the page. So if you were looking at the current through this winding around this tooth right here, you'd see that the current goes into the page here, wraps behind this tooth, comes out the page here, and wraps in front of this tooth here. And that defines that winding around this tooth. Similarly for these teeth here. Now note that you can click and drag on a rotor lobe, and it moves the rotor around. Now also note that when a winding area turns green, that represents that it is firing at that time, that this phase is on. So right now phase A is on and phase B is off. Now the way the auto set button works is that it sets the angles for your firing in such a way that it always applies a clockwise torque on the motor. So for instance, at this point right here, I'm no longer applying a clockwise torque on this motor. Therefore it shuts off phase A. At this instance here, I want to use phase B to pull the rotor around again. So another cool feature is that if you set the number of turns to 0, one of the things you can do is set a % slot fill and width of winding wire, and this will automatically set the number of turns that can fit in here based upon this area and these two parameters. So for instance, if I say the % slot fill is 70%, I am saying that 70% of this area can be filled with copper. And if I say that the wire is 100 mils, you'll see that now I can fit 45 turns with a 70% fill in this area, and with the wire being 100 mils. Now note that this will automatically update when you change any parameter that changes this area. So for instance, if I were to change the height of that tooth to, instead of 70% to, let's go 40%, that is going to reduce my area and thus reduce the number of turns that I can fit in that area. So we just saw it move from 45 turns to 24. So let's go ahead and change that back. Now, once you go over to the Finite Element tab, here you define the material for the stator, the rotor, the air, and the coil, or the windings. So by default, the stator and the rotor will be this M19 steel. If you wanted to look at what the actual characteristics of this metal is, you can just click this view button and you see this form will pop up that will describe what the actual pH curve is and define the other properties of the metal. Now, FEMM comes with a number of materials that you can use. So if you hit this Add from Library button, you can go through here and find some other type of material and add it to this list. Once you add it to this list, it'll automatically appear in these drop-down boxes that you can use for the stator, rotor, winding, and air gap. So once you have this material set, you're all ready to analyze. So all you have to do is hit this Analyze button. Now, when you hit this Analyze button, two files will be generated. An FEMM file that basically takes all of the physical dimensions of this motor and all the winding information and puts it into a format that FEMM can read. And it also generates this script file that will tell FEMM to load this file and analyze it, mesh it, and analyze it. So if I hit this button, then the FEMM program should pop up and it should start analyzing it. Now note that QuickMotor really is just an interface into FEMM. FEMM does all the finite element analysis and all the really hard computation. Also note that this is running on a virtual machine, so it's going to be quite a bit slower than what your desktop should run. Okay, so once FEMM has finished, you will see the actual flux lines, and you'll have flux densities in through here. Probably the most common thing that you'll be doing is you'll be looking at what the torque acting on the rotor is. So to find the torque acting on the rotor, the first step is to select the rotor itself. So you have to make sure that this button is depressed and you click on the rotor and it will select that block. Now you want to perform a block integral on this on the rotor. So you hit this integral sign and you come down here to torque via weighted stress tensor. Hit OK, and it'll tell you right here that this is the amount of torque acting on your rotor is a negative 31.8 Newton meters. So there you go. That's how you find the torque acting on the rotor. Note that this rotor is in the exact same position as this rotor. So if I were to move this rotor around and then reanalyze it, this rotor will have changed. So also note that there's a few other things that actually, there's quite a few other things that you can do in FEMM to help you analyze your design, but we'll save that for a later video. So thank you for using Quick Machines, and I guess I'll see you in later tutorials.